Welcome back to today's video. In this video, we're going to introduce scalar products. Now, in previous videos, we have talked about norms and metrics in vector spaces. And we've also said that we wanted to measure length and distances and also angles. So the angles are the one point that's still missing. And we need scalar products to do just that. However, the connection will not be visible immediately. And actually, we'll defer that point until a little later. Instead, we'll introduce scalar products in a way that makes the connections to norms and metrics more clear. So we'll first use an abstract introduction into that topic, and then later discuss how we can actually use this to measure angles. So this section is called Scalar Products. And let's dive right into the definition. Just one quick word of warning before we do that. The name scalar product is similar to the scalar multiplication operation in vector spaces. Please do not confuse those two. They don't have a lot in common, actually. So we're going to start with a vector space. So let V be a vector space. And again, we'll define a scalar product as a function on a vector space that has a number of properties. And then we'll have a look at how the usual scalar product on R to the n works. You can, of course, keep that in mind if you know that from school already. That's the most prominent example that we often use. But there are other scalar products, and sometimes it's useful to deviate from that standard scalar product a little. Also, the properties that we're going to discuss will be important for working with scalar products, so you need to keep those in mind. Okay, a function, we'll call it S for the moment, and a scalar product, there will be a function that takes two vectors as an input and assigns a scalar as an output. So you want a function that takes two vectors, v times v, and assigns a scalar as an output. Similar to what the distance did, but with very different properties. So that is called a scalar product, or sometimes also an inner product. On V if it has the following properties. Now we want the following things. First thing, the scalar product does not necessarily have to be non-negative. But if we measure the scalar product between a vector and itself, we want it to be non-negative. So S of x and x is greater or equal to 0 for all x in V. And in addition, we want that specific scalar product to be equal to 0 if and only if x is the 0 vector. And you will find the scalar product usually does take into account the direction of a vector. Yeah, the norm doesn't do that, of course. The distance also. But for the scalar product, the direction is important. But if you take a vector and then compute the scalar product of the vector with itself, we want that to be non-negative. And why this is important, we'll find out in just a few minutes. Second property, we want the scalar product to be symmetric. So we want the scalar product of x and y to be the same as that of y and x for all x and y in V. And finally, and that's probably the most important and the most prominent property here, we want the scalar product to have kind of a linearity. But the scalar product takes two vectors as their inputs. A linear function usually takes only one. And what we want is, we want the scalar product to be linear in each of those two components separately. So, expressed as a formula, we want S of lambda x plus mu y, comma z, so the scalar product of a linear combination of x and y with some vector z, we want that to be the same as, and now we just keep that z fixed and just apply linearity with respect to that first argument here. And that yields lambda s of x and z plus mu s of y and z. So actually I did two steps at once, of course. First step would be something like this is s of lambda x and z plus s of mu y and z. So that's the first part of linearity. You can take out the plus here. And then again, you keep the set fixed in both of these. And you get that. You can also take out the constant vector, the scalar lambda and the scalar mu. And that needs to hold for all x, y, z in V, and all lambda mu in the reals. Now those are the three properties that we want of a scalar product. I've said that we want linearity in both components separately before, yet we've only defined it in one here. And that's because the other one is immediate by this second property. Remember, the scalar product is symmetric. So if you want linearity in that second component, we can just switch that to be the first and then apply this property, right? And actually this property has a name that is called Bi-Linearity of the scalar product, right? So it's linear in both of its components. That's why we call it bilinear. Again, because scalar products are so often used, there is a special notation for those. Actually, there's more than just one special notation, but we use mostly this one here. We'll usually denote a scalar product as the following. So the scalar product of two vectors s and y, that will be denoted by the notation x, comma y, and then we put this in angle brackets like this. So this is the notation that I'm going to use for the scalar product. You may be used to something like x circle y like this. I don't particularly like this because that circle is usually used for the concatenation of functions, whereas this notation here doesn't have, at least not a lot of other uses. Right? So this is what I'm usually going to use for the scalar product, and of course my advice is for you to do the same. Again, on R to the n, there is a very prominent scalar product, and that's the one we most often use. So on R to the n, a scalar product is defined by saying, well, if we have vectors x1 to xn and y1 to yn, and we want their scalar product, then we can compute that by taking the product of these single components and then summing those up. So what we do is we compute xy, x1 times y1, then we add xy times y2, and so on up to xn times yn. This is called the canonical scalar product, and this can be written in a very neat way using matrix multiplication. This is the same thing as taking x as a row vector and then multiplying this with the column vector y. So this is the same as x transpose row vector times y. And that is actually what we use most of the time. We use this matrix multiplication notation very often in connection with scalar products. And this is called the so-called canonical or Euclidean scalar product. And finally, a vector space, any vector space equipped with a scalar product, is also known as an inner product space. Or if the vector space is also finite dimensional, that's going to be the case that we consider most of the time, then we'll speak about a Euclidean vector space. So a vector space equipped with a scalar product is referred to as an inner product space. If V is finite dimensional and has a scalar product, it will be called a Euclidean space. Or Euclidean vector space. And that's our usual case. The Euclidean vector space, just think of R to the n as the most prominent example, equipped with the canonical scalar product. Now, I already said we'll be introducing a scalar product this way because I want to emphasize the connection between scalar products, norms, and distances. And let's just see what this connection is. That's a first theorem here. Now, if we have a scalar product, then you know already by the first property, the scalar product of a vector and itself is always non-negative. So we can use that as the basis to define a norm. And that's just what we'll do. And so that the norm properties are satisfied and the connections all work nicely, we can't take that value right away. Instead, we'll take the square root of that value. So, oops. A scalar product, and we'll write that in this form. So that's a general scalar product. Induces a norm like this through the following definition. The norm of a vector x is defined as the square root of the scalar product of x with itself. And in particular, you notice this works for the canonical scalar product, which induces the Euclidean norm. So in particular, the canonical scalar product on R to the n induces the Euclidean norm. So if we take a vector x1 to xn, compute the scalar product of that with itself, and then take the square root of this. Well, what is that? Well, that's the square root of x1 times x1, so x1 squared, plus x2 times x2, x2 squared, plus, and so on, up to xn squared. And you can see this is exactly the Euclidean norm of x. So this is the connection. If you have a scalar product in a vector space, that's the strongest property that you can have here. A scalar product induces a norm induces symmetric. So once you have a scalar product, you have everything else. Right? So that's the chain of command, so to say. If you have a scalar product, then you automatically get a norm. And we've seen already, if you have a norm, then you already get a metric as well. So there are spaces that have a metric but no norm that induces them. We've seen the discrete metric. There are spaces that have a norm but no scalar product that induces them. And then there are spaces, and that's most of the examples we'll be looking at, that have a scalar product, and that induces the other two, a norm and a metric, that work together. And how they work together, that's part 2 of that theorem. That's one of the ways they work together. If you have a scalar product and you look at that and the norm induced by that scalar product, then those are related by an inequality that will often be very handy. So we write that down. For a scalar product, we'll denote in that usual way here, using this angle brackets. And the induced norm, that again will be written in the usual way. The so-called Cauchy-Schwarz inequality holds. Or short form for that, we'll often refer to that as the CSU, or CSI. CSU is the German abbreviation, the Cauchy-Schwarz Ungleichung. So if I happen to say CSU, I actually mean CSI. So that's the Cauchy-Schwarz inequality. And that holds in those spaces. And it says the following, very easy to remember. Take a scalar product of x and y, any two vectors. Then this is always less or equal to the norm of x times the norm of y. And this even holds for the absolute value, right? For the norms, the signs don't really matter. So whether I take x or minus x doesn't make a difference. For the scalar product, that might be different, but of course, if it's negative, it's even lower. So we can take the absolute values here. And this holds with equality if and only if x and y are linearly dependent vectors. With equality, if and only if x, y is a linearly dependent set. So basically, if x is a multiple of y, then this holds with equality. Otherwise, it holds with strict inequality. Now, we're going to have a look at the proof of this inequality here, mainly to show you how to work with scalar products using these abstract definitions that we had in the definition of a scalar product. Remember, 3 properties. First, we have this one here, scalar product with itself, a vector with itself, is non-negative. 0 exactly if x is a 0 vector. Then we have symmetry, that's hopefully easy to remember. And then we have linearity in each component. So you fix one component, you have a linear function in the other. And to get used to that, we'll have a look at the proof of the Cauchy-Schwarz inequality. Okay, so the first case we'll have to look at is, what about the case where y equals the 0 vector? That's an easy case for y equals the 0 vector. What we have is the scalar product of x with that 0 vector is, well, that's the same thing as x with 0 times the 0 vector. And by bilinearity, we can take that 0 out. So that's the same thing as 0 times that scalar product here. And of course, 0 times any real number is always 0. So the left-hand side of that inequality is 0. Let me just write down the inequality once again so that you can see what we're working with here. Okay, so for that case, this is 0. And of course, the norm of y is also 0. So the right-hand side also becomes 0. So as this norm is 0 as well, what we have is the right-hand side is also 0. And that means both sides are equal. So second case, we can now assume that y is not the 0 vector. And in that case, of course, the norm of y is strictly positive. So we can have a look at a linear combination of x and some multiple of y. And we later set that multiple suitably. So the idea is, for any lambda in R, we hence get the following. We can have a look at the scalar product of x minus lambda y with itself. That's a scalar product of a vector with itself. So that means that's always non-negative. Right? First property of scalar products. Now we can use the second property, the bilinearity property, and decompose that. Let's first apply linearity to the first component. So that means we'll keep that second component here, we'll keep that fixed, and we'll apply linearity here. And that means what we get is x, and the second component is kept fixed, minus lambda times y, and again the second component is kept fixed, right? So this component here is always fixed. And then using symmetry, we can also apply linearity to the second component. So let's do that. Now we keep this here fixed first. And that means we get x and x minus lambda x and y. So that was these x factors that are kept fixed here. And for the second, we keep this y here fixed. And what we get then is first minus lambda scalar product of y and x. And then we have the minus lambda again, so that's plus lambda squared scalar product of y and y. And here's the fixed y, and here's the fixed y. So that is, well, the scalar product of x with itself, that is basically the norm of x squared. So we can abbreviate that as norm of x squared. Then we have minus lambda scalar product of x and y minus lambda scalar product of y and x. By symmetry, those two are the same. So that is just minus 2 lambda scalar product of x and y. And finally, we have here lambda squared times the norm of y squared. And now we're going to use a very special setting for this lambda. And here we need to know that the norm of y is not 0. So, thus, if we set lambda to the scalar product of x and y divided by the norm of y squared, what happens? And remember, we can do that because this is by our assumption not 0. That's why we had to do the first case, y equals 0 first. Okay, we obtain the following. Well, we already had 0 is less or equal to, and this is this point. We started here, and we obtained this one here. So let's copy that basically and substitute the lambda. So we have x norm squared, no lambda in there, minus 2 times, let's substitute the lambda here. So this expression is the lambda, right? Times x, y. Plus, and then we have lambda squared even. So that means we have x, y squared divided by norm of lambda to the power of 4 times norm of y to the power of 4 times norm of y to the power of 2. Okay, so that's what we get here. So this here is our lambda, or lambda squared in this case. Now let's try to simplify this a little. What do we get if we simplify this? Well, the x norm squared, there's nothing to simplify here. So in this case, well, we just get, this is 2 times the scalar product squared over the norm of y squared. Here we can simplify a little. Right? We have this norm of y that cancels out, or at least part of it cancels out. So we get scalar product of x and y squared over the norm of y squared. And now you can see this expression here, this expression here is the same as this one. So we can simplify a little more, and we have x norm squared minus just 1 time this expression here, scalar product squared over y norm squared. And now let's reformulate that a little. So what we do is we take this here to the left, and then we get the scalar product squared over y norm squared is less or equal to the norm of x squared. And then of course we can multiply with its denominator here. And that yields xy scalar product squared is less or equal to x norm squared times y norm squared. And that is the squared version of this inequality. So by just taking the square roots, we can then be sure that this inequality, the CSI, actually holds. So this completes the proof. And as you saw, we worked with the first property of the scalar product, we worked with some properties of the norm, and we worked with the bilinearity. That was the most important one here. Okay, so that concludes our introduction into scalar products. In one of the next videos, we'll have a look at a connection between scalar products and matrices, and then we'll start applying the scalar product to talk about angles. And the first case that we'll talk about is orthogonality. So we first have a look at orthogonal vectors, and then later on we'll extend that to arbitrary angles. And as usual, I hope to see you then.